Okay. Very happy to have here today Yossi Keshet. Yossi was a research faculty member at TTI a long, long time ago, and is coming back to visit us. He is currently an associate professor at the Technion. He's well known for his work sort of straddling the boundary between machine learning and speech, as well as building very neat tools for linguistic measurements and human signal measurements. Today he'll be talking to us about diffusion models. Take it away.
So this is actually, I'm going to describe two of my recent works. They are both on diffusion model. The first, maybe third, maybe a quarter of the talk is about text-to-speech, which is an autoregressive model, and it's a very practical, and it raised many questions. And most of the talk I would like to spend on the second part, which is theoretical analysis of diffusion models in the spectral domain, because we had a problem in the first work about some high frequencies. So I really would like to have to see what they think about the second work. It has many issues. So it was done with my student Roy Benita. It's a joint student of mine and my professor Miki Elad, also from the Technion. So I will start with just a background and notation, and I guess you know diffusion model, and if not, I'll do my 5 minutes tutorial on diffusion model. So we assume that we have a generating process. We call it a forward process. So we assume we have a signal, let's call it x naught, x0, and the forward Markovian process is like adding, contaminating the signal with noise gradually until we get xt at t steps, which xt is completely Gaussian. And here in the equation we see it's a linear equation between the previous x and the current x, and epsilon theta is a isotropic Gaussian noise. Alpha are called the incremental noise schedule, and an alternative form for this equation is just going back from any xt to x naught, and this is by changing the alpha, and we call them alpha bar. Some notation has alpha and beta, and here it's alpha bar. But I want to stress and say that those alpha bar, they are called the noise schedule. Just the alpha is the incremental, but I will focus on the noise schedule because I want to find them optimally later in the talk. So they are the mechanism how to gradually add the noise. Okay. So this is the forward process. No learning is taken here. Just a random process. And then we have the reverse process. One process called DDPM. And in this process, we try to, it's a generative process, and we try to do the opposite, coming from xt complete noise to a signal, and we do it gradually by learning a denoiser epsilon theta. Epsilon theta is a deep neural network or other learning mechanism, and here sigma is a multiplier. It's the standard deviation of the noise. Z is also isotropic Gaussian noise. So this formulation is a stochastic formulation. There is another formulation for that, DDIM, and it was proposed by Song and colleagues in 2021. Where the process is deterministic, and again it assumes that we have a learned epsilon theta. There is no noise here. It's supposed to be more efficient mechanism to generate the reverse process. So just to mention, in DDPM we use the notation T and capital T. And for DDIM, I use the notation S and capital S. Those are the diffusion times. And we have also speech, and speech has its own timing. I hope it will not be confused. it's not be confusing. So I'll start with the first work, which autoregressive diffusion model for raw waveform generation. So our goal, it's called DiffAR, Diffusion AR, autoregressive, and our goal here is to create high quality speech with some qualities, voice qualities that are not preserved in the current systems. This system is from 2024. Now there are better systems. It's really hard to keep the gap here. But this was started from a joint work with Jennifer Cole. She wanted to somehow generate speech with any pitch contour. The idea was to create an amazing speech that instead of having somebody to record the speech with different pitch contours and then ask human listeners what they think about that, is that a question, is that a statement, and so on, we want to do it automatically. This work was not successful, but we have this paper that was successful. So we want to have some qualities that we don't have in current system. We also want to have stochasticity, so it means that every generation of the speech will be quite different. And one of the things we want to have is voice qualities such as vocal fry, and I'll show it a little bit later. So currently there are two types of approach. One of them is having text and using a decoder. The decoder is a mechanism to learn a spectrogram, or often a MEL spectrogram. And in order to playback this, we need to go in order to generate a waveform, we need to go through a vocoder. Vocoder is a mechanism to add a phase, because if you remember, the spectrogram is a complex number, and we need to add a phase in order to go back to the waveform. So this is the goal of the vocoder, and those system has several problems.
So you're looking at the spectrum as over the complex or of the reals?
No, this is the reals. There
I
are
thought you said the spectrum is complex. Sorry, okay.
There are few works that works on the complex.
Okay, that's fine. I thought you said that you're looking at complex spectrum.
No.
The spectrum is complex. Sorry.
And usually, often the spectrogram goes by windows of 20 milliseconds. Vocal fry, for example, I can't do that. Sorry, with my Hebrew accent. But vocal fry, I guess you know that vocal fry or a creaky voice. When young women say, "I don't want to do that," I can't do that. But the Kardashians and everybody can speak like that. And this is like, instead of the vocal cord moving, it's like the lower part of the false vocal cord are moving. And now it's like every girl and every young male speak like that in the US and in Israel and all over the world. The thing is that it's like a very long-term phenomena, and you cannot synthesize speech when you work with 20 millisecond frames or 25 or whatever. We need much longer frames. So the code.
I have a question.
Yeah.
So for those that are not sufficiently familiar with the speech generation domain. So first so you have the spectrogram, and then you have the red thing on the right. I guess that's this one-dimensional acoustic waveform.
This is one-dimensional acoustic waveform.
And that is eventually what you need to generate?
This is what I need to generate. This is like every 20 milliseconds, 10 milliseconds,
Right.
25 milliseconds.
So spectrogram.
You take FFT. It's FFT.
Right. So the spectrogram in principle contains enough information about the sound. Can you play the spectrogram? Can you just directly?
No, you cannot play that directly. You need
So
a
vocoder is what plays the spectrogram essentially.
Yes, you need to go back to the original signal. You need the phase, because the spectrogram is not actually the FFT. It's the magnitude, the amplitude of the FFT. It's the.
As a spectrogram is just the energy contained in various bands of frequency.
Yeah, but the FFT is a complex number, so you miss one number here. We need in order to go back to do the inverse FFT, we need the other number.
Just to clarify,
phase or the imaginary.
Actually, just to clarify, if you had a complex spectrogram, so if you had for every time and every frequency level, you had a complex number, then you could then it would be a one-to-one, right? But the things you have a projection of that, so you're missing information. You have to make
right. But the notion of spectrogram is actually not complex. It's using the amplitude of this number. I don't know what, I don't think we have any notion of the complex number itself. We always have meaning to the amplitude there. So this has problems. It's also had a vocoder is something that is trained on a different set. There is a problem with this vocoder. There is another approach. So I'm reviewing what is done is end-to-end approach and modeling directly the signal. But currently the method having directly modeling the signal, it's like modeling 1 second of speech, and there are other models, but since this work, but that work, at the time of that work, it was only 1 second of speech, and it was limited, and we wanted to extend that to any length of speech. So our goal is to generate a diffusion probabilistic model end-to-end to directly model the waveform, and we don't want to be a fixed length, and we want extremely long text. And this is a problem. I'm trying to show it here. Extreme long text is what you see here is the number of words at the input and the used GPU memory. And our method is in the blue that I will describe. But other generation methods, WaveGrad 2 and Fast Speech, which are really great, has exponential usage of memory. And they don't tackle the problem of how we generate a long sequence. So I will go back to that, but our method has much more CPU usage compared to those two. Okay, so let me describe that. Again, I would like to focus on the other work, which is more theoretical, and this is just a practical issue with that. So we would like to generate a signal of length L, and we would like to break the work into small frames. But again, I don't want to use 20, 25, 10 milliseconds. I would like to use, which are 20 milliseconds, it's the stationary frame of speech. So we would like to do something else. We would like to take 500 milliseconds here, which in 500 milliseconds, it's like a word, a half a word. And then we would like to use a diffusion model that will generate each frame, but will be dependent on the previous frame. So what you see here is XL, it's the current frame. L, the superscript L is the timing of speech, it's the frame number. And XL-1 is the previous frame. And what we do here is actually modeling the current frame given a portion of the previous frame. So it goes like that. This is the original speech. 500 milliseconds. We take part of this, it's 200 milliseconds. Kennedy is almost a word. We take this part, and this is the generated part. This is the generated part, and what we do is we are based on the previous one, but we generate everything from scratch. So if you look carefully, those are not the same. And if you look carefully, the generated speech is not the same as the original speech. By the way, this is vocal fry. You see, it's not the pitch is not it's not aligned correctly there. Anyway, so we take that signal. We would like to take an overlap data, put it into the model, and generate the speech. So what we do is we can write it mathematically as H, which is a matrix that defines the previous frame, multiplied by the previous generated frame, and put it into our diffusion model and generate the next frame. So practically, we built a denoiser. The denoiser gets as input the T, the time of the diffusion, the current frame that we would like to generate. YL is a representation of the text, and we also get it as input the previous frame. And we would like to estimate the noise that will add to the signal, that will add to the signal to remove the actual noise. So this is our model. We train it on the L2 loss, as usual in diffusion model. This is DDPM. So we train epsilon theta, which is based on the equation that you saw earlier of DDPM. This is the equation of generating xt based on the x naught. on the L frame. We also have as input the previous frame, the actual part of the previous frame, the textual input represented as phonemes and durations. I will show it in a moment. And then the T, which is the diffusion time, would like to be as close as possible to the actual noise. And our inference is presented in the other equation. It's the standard equation of diffusion, except that there is dependencies of the previous phoneme. Our model is as follows. It's yes.
Sorry, quick question. So YL is the text input. Is that correct?
Right. So YL is the text input, but so the text input go to a graph into phoneme, which then gets to two other models, which is the energy prediction of each phoneme and the duration prediction for each phoneme. We have the pitch for Jennifer Cole, but we leave it now because it works, but it wasn't as we expected it to work. And we have the previous frame. Those enter to a model called MRB. It's just a multi-scale convolutional, 3D convolutional network. And it's a type of complex unit. I will not get into why we choose this architecture and the reason for that, but it's based on several architectures. But we have the text. The text go to a phoneme representation. The phoneme representation is actually also unique, but again, I will not go into that. It's just technical details.
Sorry, Yossi. So YL is the phone label of frame L.
Right.
And so you a priori decide on the alignment between the phone
Yeah, this is a big
sequence.
issue. This is actually aligned to phonemes. So I said that it's 500 milliseconds, and then we have overlap of 200. This is not a fixed 200. It depends on the size of the phoneme. We want to have a fixed amount of phonemes between 1 and 3. So it will be aligned with the phonemes, not split the phonemes in the middle.
So how do you decide on the duration of each phoneme?
We
Duration.
have a
Okay.
duration predictor. It doesn't work without that.
Okay.
It doesn't work without the energy predictor, although we know that BGT, PTK have low energy compared to the vowels, but it doesn't work without that.
But the alignment is not the diffusion process is not adjusting the alignment. The alignment is fixed somehow.
The alignment is generated automatically. So we have the text, we have we generate phonemes.
The diffusion process is just on the output signal. It's just
Right.
on the waveform.
Right, yes. Not on the alignment. This is the alignment. The duration model is actually not. There is no stochasticity in the duration model. It's
Can you say
fixed.
something about the duration model? Like, is it learned or?
It's learned. Yeah, those are learned. The energy predictor and the duration predictor, they are learned. They are learned actually end to end. They are learned with the
diffusion process.
with the diffusion. Yeah, they are learned everything together.
See.
And the goal is to generate a signal at the end, which will match the signal at the input.
So there's no control over like the speaking rate. It's just whatever it learned
No,
from
this was done.
distribution of the
Yes,
training data. Okay.
this was done on purpose. I guess we can add that. We actually do that now for another work. This could be done technically. And the results are back at that time, 2024. Everything moves so fast. So we outperform other systems. So WaveGrad, it's a system which is based on flow matching. VITS, it's a variational autoencoder, which is autoregressive. This is the only one which is autoregressive somehow. Grad TTS, what is Grad? Grad TTS is text encoder, like transformer text encoder, and then DDPM on the top of that. And then there is unit and evocoder. So Grad TTS is with vocoder. DiffGAN is diffusion and GAN together and with a vocoder. Those were the state-of-the-art system, and what we see here is a measurement of Mushra, which is asking human listeners to compare between our system, DiffAR, and the other system. Like it's A/B testing, and it means that 69% of the time, human listeners, it's about 10 listeners for each file here. 69% of the time, human listeners prefer our system against, I don't know, Diffusion, TTS. I think now there are better systems, or we don't really know what's out there. What you see here is the stochasticity. So what you see here is our system, VITS and Diffusion TTS, and you see the pitch and the intensity. The red is the original signal, and you don't see it very clearly, but you see there are many blue signals. It means that every generation, every inference of the DiffAR is different, a little bit different. Whereas in Diff, it's almost the same, it's just a shift of time. And in Diffcom, it's completely the same. So we have a stochasticity here. Again, it's only in the signal and not in the actual phoneme duration or phoneme energy. We could generate vocal fry, which was one of the goals in this work. Vocal fry is the mechanism that caused, again, the vocal fold to vibrate differently. And you can look, it looks like an irregularity in the speech. So compared to this part, which is regular, this is not regular. And our system can...
Anybody here do that? I don't know what that is.
I'll give it a shot later.
This is, I will play that. This is labeled by red here. Okay.
Play it again.
I didn't hear any.
It's yes. Let me.
Everybody all together now.
Yes.
I'm not sure even what I'm supposed to be.
Listen North American, listen American live.
I'll show you another example of
It's all right.
she speaks like that.
That was.
It's really nice. But let me go back to my presentation. Anyway, our system is the only one who can do that because of the sorry, it's wrong presentation. Again, it's part of a work of generating speech that could be used in phonological research. So anyway, our system, it's the only one we saw that could generate that. Here are some examples. Again, it's trained on Linda Johnson's speech, which is she natively sounds very synthetically. Okay, so this is my first work, but I would like to focus on the second work, which is more theoretical and more interesting, in my opinion. Any question about this work?
Two quick ones. What's the time resolution you're generating? Like 1 millisecond? You're generating a signal, but it's some.
We generate 500 milliseconds altogether.
At what resolution?
What resolution? We generate 1600 kilohertz, so it's 16,000 samples.
Okay.
We generate the raw waveform.
How many steps of, so that's what, okay.
Okay,
How many steps of diffusion do you do?
I'm sorry. So we have 200 steps or 1,000 steps.
Of diffusion?
Of diffusion, it's huge. We didn't try DDIM and we didn't try to make it more efficient, although there's...
What's the architecture of your epsilon network?
This is what I showed earlier. It's a kind of a unit. It's based on blocks. Those are 3 convolutional layers that get the inputs.
I see.
And then we are fully connected. And the whole thing here is n layers. We have, it's 8 layers here, and here we have, this is 3 layers, each of them.
Okay, it's a form of UNet. I guess that's what I was asking.
Yeah, yeah.
Okay.
Okay. So Roy wanted to continue with this work, and the idea was to have long in-painting. So it means that we have a portion of speech, let's say 500 milliseconds removed, and we would like to reconstruct them. Really long, very long in-painting. So we tried to do it with the previous system, it doesn't work. So what we did is we decided to go with the pyramidal version of that and try to generate, let's say, 4 kilohertz, generate the signal, and then have a super resolution diffusion model, and then regenerate at 8 kilohertz, and then go to 16 kilohertz, and so on. And this was unsuccessful as well. What we saw with this method is actually that high frequencies were not generated. Like going to the last, like from 8 kilohertz, high frequencies are not generated correctly. So what you see here is the original signal. This is between 0 and 8 kilohertz because it's sampled at 16 kilohertz. And this is FFT of one portion here. And this is the generated signal. So you see a line here, and you see that the upper part is not generated correctly. You see it here. We thought it's a bug, but it's not. It's actually something that happened a lot, and there are a lot of papers about that. I mentioned 3 here, which state that formally, but there are other papers. In Vision, it showed that it's stated like the picture is not sharp enough, and there are methods to show that. In speech, it's a known fact, and we have 3 papers here. The first 2 claim that this is known. What you see is a graph of the first paper, and you see that the correct model it's a dotted blue. In the middle there is dotted blue, and this is the frequencies between 0.2 and 0.5. It's normalized frequencies. And you see that sometimes the mid frequencies are off, sometimes the high frequencies are off. This first paper tried to use many diffusion models to see this phenomena. The second paper just state that and show it empirically. The third paper state this claim and say, okay, let's go to the spectrum and try to do diffusion model on the spectrum and show you that this phenomena is fixed, and it's make things really better. But we ask ourselves how come high frequencies are not generated correctly? Is that our architecture, or maybe it's the diffusion model, because diffusion model is a mathematical formulation that's supposed to be correct. So our goal is to analyze diffusion model using frequency response. So frequency response is the following: is like for every it's about the system, and we would like to analyze the system in terms of the frequencies. So what you see in the x-axis is like the input. So those are the input frequency, and what you see in the y is the value, the amplitude of the output frequencies. So in this example, the output frequencies are 1 until you get to some cutoff frequency, and then they go they are lower. And this is a low-pass filter, but this is a way to define a system in terms of its spectral content. So we would like to do the same thing for the diffusion model, to see a given input, given a specific frequency input, what is the frequency of the output, if there is a degradation of the frequency or not. And again, the challenge is to separate the diffusion process from the specific denoiser, from the specific architecture here. We assume, okay, so is it clear the goal? Try to emphasize. So we assume multivariate Gaussian input, and we derive an optimal denoiser analytically, okay? And there is a byproduct for this analysis, the byproduct is that we could actually find an optimal mechanism to find noise scheduling. So noise scheduling are those alphas that we could use to generate the speech. So this is examples of those are examples of noise scheduling. So what you see here is like 250 diffusion steps, and those are the alpha proposed by heuristics. One of them is called sigmoid, for example, and it's a curve that says how do you pick the alpha along the diffusion process. Again, they were selected by heuristics. They are good, but there is no analytical mechanism to select them. Okay, so I'll start with an assumption. The assumption again is that our signal is drawn from a Gaussian multivariate distribution with mu fs and sigma mu 0 and sigma 0. Okay, the signal are drawn from this distribution. This is an assumption that is used in several diffusion models, several papers of analyzing diffusion models. And the first theorem, it's really known fact that the optimal denoiser is a winner filter. So what we do here is the optimal denoiser in terms of MMSE or in terms of map. I'll show that in terms of the map estimator. So we would like to maximize, to find x0, x0 that will maximize the log probability of x0 given xs. xs is the final signal, it's completely noise, and x0 is the target signal. So we would like to find x0, okay? So using Bayes rule, we can decompose the probability, and we can then we can plug in our assumption that p x0 is from Gaussian distribution, and then we can plug in the conditional probability that x0 given x0 is also defined because we know the forward process of diffusion models. So it's given by a known formula, right? Xs is given by a square root of alpha s times x0 and the scaled version of the noise. Okay, so if you plug in this, you can actually find it, find the probability, and you can differentiate with respect to x0 and compare to 0, and then you get this equation. This equation means that for any target image, for any target speech x0, it's a linear combination of any signal along the diffusion, okay? So we can go back and forth, it's linear, everything is known, it's not a specific architecture here, and it's winner filter. Okay, with that we continue, and we said what is the reverse process, DDIM. So we use the formula of DDIM. This is the forward process, and we can plug in our epsilon. So we do that by just changing the order and finding what x0 is, and plugging it back to the equation. And if you just do the mathematics here, we get this formulation, which is the process. It's defining the reverse process, but again, this is in the time domain. Everything is linear here because we assume, again, x0 is drawn from a Gaussian distribution. Okay, let's continue with that. We would like to go to the spectral domain. So again, we assume, as you remember, we assume that x0 is drawn from a normal distribution. This is x0, it has 8 samples, maybe it's a speech signal. And then we would like to take the DFT, the discrete Fourier transform of that. Again, it's 8 numbers, those numbers are complex. Okay, and we denote that with x0 with a capital F, calligraphic F, okay? We can also write it as a multiplication of a matrix F times the x0. Okay, if you assume a circulant matrix, okay, if you assume that sigma 0 is a circulant matrix, the eigenvector of sigma 0 are actually the Fourier basis. of the signal, and the eigenvalues are the Fourier coefficient. And this is nice because we can use that to have another matrix. So if we have Fourier times the covariance matrix, and this covariance matrix is circulant times Fourier transpose, we have another matrix. This matrix is diagonal. The elements on the diagonal are Fourier coefficients. Those are the eigenvalues of this matrix. And this is interesting because those are the frequencies. This is the lowest frequency, and this is the highest frequency. And this is what we want to do. We want to analyze those frequencies. We want to see what happens to those frequencies. Okay. So now we move to the spectral domain. We move to the spectral domain again by applying Fourier transform. So we do it on the reverse process that you saw earlier. We just apply. I'll show it momentarily. We multiply it by f, from each side of the formula. From this, we can go back to if we apply this equation iteratively, we can go from the x naught, from the target signal, to the noisy signal. And this is actually the transfer function we were looking for. So x0 is the target signal, xs is completely noise. And we have two elements here, d1 and d2. D1 and D2 depends on those alphas and nothing more. XS is completely Gaussian. U0 capital F is the Fourier transform of the original U that the signal was generated from. Okay. If we look at this formula, we know that x naught in the Fourier domain was generated also as Gaussian signal with the mean of D2 mu0 and variance of the covariance of D1 square. Okay, the way I got into that is as follows. We just apply Fourier, so it means that it's really easy. We apply Fourier on both sides, so we multiply by this matrix F, and if we add FTF, because this is I matrix, in several places, we could actually change F sigma 0 F transpose to the lambda 0 matrix, and we can get the desired result. Okay, so again, what we had here is a transfer function, assuming Gaussian noise, between the target signal and the noisy signal. This is for DDIM. We have the same thing for DDPM assuming input noise, and this is also a transfer function, a Fourier frequency response of the DDPM process. Okay, this is where we left it here, and I'm going to show you an application of that, of using this mechanism. So, and we will go to this a little bit later. So what we did here again is just formulating it as a frequency response. So I'm going to remind you, we have an assumption that x0 is Gaussian. We found that the generated signal is also Gaussian, but a little bit different. Okay, the first row, mu0 and lambda 0. And the second one is we do D2 mu0 and D1 square. And we can actually use those to find the alpha, the optimal scheduling. D2 and D1 depend only on alpha, the scheduling parameter. So what we can do is we can define some distance between those probabilities, D. It can be KL divergence, it can be a different distance, and we can try to minimize the distance between the diffusion process generated signal and the original signal. And we minimize that in relate to alpha. So we can find alpha which optimize this distance. We also need to have a constraint that the first alpha will be 1 minus 0 epsilon 0, and the last alpha will be very small, maybe 0. and we need that the alpha will always decrease, and that's it. So again, we can solve it for finding the optimal parameters. Yes.
So what's x hat here?
X hat is the generated signal. It's like x0. It's I just wrote it x hat because it's generated from the diffusion process. This is the actual target signal. We know it's from Gaussian distribution. This is generated, so it's not exactly it's just a notation. X hat is the generated image, the generated speech. X0 is maybe the original target speech. Okay, we try to minimize the probability between them. Okay, so we look at two distances, the KL divergence and the Wasserstein two distances, and because everything is Gaussian here, we can actually have analytical terms into those distances. Lambda I are the eigenvalues of the original covariance matrix. D1 and D2 are the elements of X naught hat. Okay, so we can find them analytically, and then we can just solve it using solving this equation using a numerical package, and see what we get. So this is what we get. So first we use artificial Gaussian distribution. This is sigma 0. It is circulant, and we can solve it for Wasserstein 2. And what you see here is the solution for each of the diffusion steps, like 10 diffusion step, 334 diffusion step. Those numbers are taken from a paper that actually used to compare all the noise scheduling parameters. So we go with that and use the same number of diffusion steps. It doesn't mean anything. And this is for DDIM. What's interesting here is that it's really coincide with another noise scheduling. So ours is the dash here, and it's coincide with something called sigmoid 1.35, the brown one. Again, our system is maybe the first one to find the optimal scheduling parameters from the signal, although we assume this is Gaussian. What you see here is the Wasserstein distance, is our goal of minimizing the distance along the total diffusion step. Our system is the lowest because we actually minimize this Wasserstein distance. Okay, you have other noise scheduling parameters. We go further from artificial Gaussian distribution. We took real data. This is music. What we did is we turned that into circulant matrix by solving some constraint. This is the circulant matrix of this problem, and you see also the eigenvalues of this matrix. This is actually the frequencies. This is a low frequency, and this is the highest frequency, 200. And again, we try to find the optimal noising parameters. Again, it coincides with another part. This is our recommendation. This is coincide with the sigmoid. This is a different sigmoid. This is 1.69. It's again known noise scheduling from the literature. And we also minimize the Wasserstein as we proposed. I'll skip that. And here it started to become more interesting. Now, instead of using our assumption that we are using Wiener filter, in those previous examples, we assumed that we use Wiener filter, so we don't have a learned denoiser. Now we use a learned denoiser. This is a unit. It's a very simple unit. It's tried to estimate epsilon theta instead of using the optimal Wiener filter that's used for Gaussian distribution. This is trying to learn the optimal signal with the neural network. We use the same noise recommendation as before. When we tried to use the noise recommendation, this was done on the Gaussian signal, but the actual application was done with the neural network. And you see here that actually the Wasserstein 2 distance is the lowest. But when we go to look at other things like Frobenius norm or FAD, which is like FID but for audio, the things were not so good. So we are not the best, and there are some other noise schedulers that are better than ours. And this raised many questions, like, again, perceptual matrices like FAD did not provide advantage. They were the same. Our system in Frobenius norm is not always the best one. There are many others that are comparable to that. And we thought that maybe there is a problem with the denoiser, which is not optimal. It's a learned denoiser, but it's not optimal to the problem. And also we use a noise scheduling, which is not optimal to the actual signal here. Yes?
Maybe I'll get to this, but how reasonable is the circulant covariance matrix assumption?
You
You will
it's
get
not.
to it. Okay, all right.
It's not, but we
Well, it corresponds to translation invariance.
sorry?
Corresponds to translation invariance. So it, I mean, if sound is translation invariant,
I think it's natively, because if you use DFT, it's supposed to be. Is this what you're asking? If you use DFT, the assumption is that the signal is repeatedly.
No, that's not what I'm talking about. So in vision, for example, you assume that the probability distribution over images is such that if I take an image and translate it in space, its probability is preserved.
Yes.
And that translation invariance can be interpreted as assuming that if the world were it's circulant matrices are related to translation.
Yes.
It sounds, if you take a sound and I play it a second later, it should have the same probability.
I think it's related to what I said we can take it offline, but I think it's related to this mechanism. That although the signal is 8 samples here, it's when you do DFT, the assumption is like if you go back, you have a repetition of the signal. So it's not that really translation, but it means that if you do DFT on the second frame here, which is exactly the same, you get the same DFT. I think.
Take it off.
I'm not sure I understand you correctly, but this assumption of how do you say that? Circulantitude. Assumption of the circulant it's not real in our life.
I mean, you could estimate the covariance matrix and compare the empirical estimate with the circulant matrix.
In a way, this is what we did here. We took a real signal, we forced it to be circulant, and we could measure how good.
Right. So how do you measure that?
We could measure. So it's Frobenius norm, for example. This is that. It's the Frobenius norm. It's the distance between this matrix and each element in the original covariance matrix.
Oh, that's the Frobenius norm you're measuring here?
Yeah, and it's Frobenius norm along the steps of the diffusion. It caused a problem. So I'm going back to what I wanted to do. I wanted actually to see what happens to the eigenvalues, to each probability, each frequency along the diffusion process. We stopped here actually. This was submitted to ICML. The paper was rejected by 2 reviewers and accepted by 2 reviewers. Completely accept and completely reject. One of the reject is like a person that did say, I'm not understanding what the paper about, I'm rejecting it. The other one said, okay, try to do it on ImageNet, try to do something which is not circulant. And we say, okay, how can we do it if it's not circulant? If it's not circulant, we don't have the Fourier, we don't have the notion of frequencies. And from this part, we are now submitting it to NeurIPS, but then we go back to our original goal, and we want to see what's going on with the eigenvalues. So what you see here is trying to solve the problem for each frequency separately. So you have 9 frequencies here, and we solve for each frequency. We solve it differently. We solve the whole problem separately. So what you see here is that yellow is high frequencies, and purple is the low frequencies. And you see that for low frequencies, the alpha goes change immediately the signal. So this means that the diffusion model really prefers to start with the low frequencies. And you see that the high frequencies don't change too much until, step 30. It's 2/3 of maybe half of the steps here. And we think this is related to this is the eigenvalues. We think that low frequency has high amplitude and high frequency has low amplitude. It means that the diffusion model really focus on the high amplitude signal, and this is also validated with experiments now. So again, you see here the different values between high magnitude frequency, which is purple, and low magnitude frequency, which is yellow. And this is something we don't know how to interpret that. We're in the process of see how it goes through time to actually try to optimize all of them together and see how lambda change over the diffusion time. This is another experiment. We looked at the error for each frequency. So again, this is circulant matrix. This is the eigenvalues, and this is the error measured by one of the lambda 0. It means from the target signal to the estimated lambda, the estimated frequency. And what you see here is that for higher frequencies we have higher error in the estimation. It means that the diffusion tries to solve the high magnitude frequencies first. Again, this is under the optimal optimal selection of noise scheduling. So this is a low frequency. It has high amplitude but small error, whereas this is a high frequency, 20, and it has low amplitude but it has very high error. The second thing I would like to mention is that we now use a better distance. Instead of using just Wasserstein 2, which is known, we try to propose a distance which scale the eigenvalues, scale the frequencies. So high frequency with low amplitude will somehow get also to be touched. And if you use this distance, what we get, again using circular matrices, we get this dotted curve here, which is coincide. This is coincide with cosine 011. This curve. And it's really interesting. It means that the heuristic selection of cosine 011 makes some sense. So what we do now, this is the actual current work, it's not future for NeurIPS, is first we try to see how the eigenvalues and frequencies goes along time. We try to solve the problem with non-circulant matrix. It means that we don't have frequencies, but we can actually use the eigenvalue decomposition, which is not frequency, frequencies, but it's spectral decomposition, and it's actually work, and we can use that for images as well. I don't have anything to show you, but this is fascinating. And the last thing we also work is trying to analyze the posterior sampling. So in inverse problems, sometimes we have samples from Y, which is drawn from some function H, a known function that was done over the original signal plus noise, and we would like to find out x0 from Y. And we can solve this in the same lines, and we also have a spectral analysis for that, and this is another work that we are trying to do. I'll try to summarize. I presented two work. One of them is diffusion for autoregressive signal that try to work on the raw waveform and work on non-stationary part of the speech and could estimate voice quality such vocal fry. And the second role, try to analyze the speech in terms of, it's not speech, it's any signal in terms of diffusion, in terms of the spectral domain, and try to build a frequency response for that. And we use application for optimal noise scheduling. And that's it. Thank you very much.
Okay, we have time for maybe one quick question, since we have another talk starting soon. What's that?
So there's another talk, right?
I know, that's why I said
That was
one
my question.
super quick one. That's your question? Yes, there's another talk. Okay, so we can take any remaining discussion offline.
Thank you very
Thanks again.
much.